Okay, thank you very much. Thank you very much for the introduction, Ricardo. This paper is about heuristics applied to solving a family of scheduling problems. I'm going to start by formulating the problem. The main motivation of the paper is that the job shop is a problem close to many real production environments. A lot of problems can be modeled by a job shop. The problem is NP hard, so it's very difficult to solve, and the additional considerations of set of times and flexibility makes the problem even harder to solve, but allows us to model some problems in a more precise way. Okay, the flexible job shop requires the scheduling of n jobs in a set of n machines or physical resources. Each job consists on a set of tasks that have to be sequentially scheduled in a pre-specified order. Each one of these tasks have to be processed in one machine. That machine will have to select it from a subset from the total of the n machines. That's the main difference between the flexible job shop and the classical job shop. In the classical job shop, each task is only processed in one possible machine. In the flexible, you can choose from a subset of machines. Okay, from this solution graph example, let us suppose that we are going to process these 4 tasks in the machine 1 in that order, these 4 tasks in machine 2 in that order, and the final task in machine 3. This is an example. And the processing time of each task depends on the particular machine. So, this would be an example of a solution graph for the flexible job shop. Now, we also consider setup times. A setup time is when a machine finishes the processing of one task and is about to start the processing of another task. A setup time is needed to reconfigure the machine. The setup time is sequence dependent, so it depends on the task that finished, the task that is about to start, and the particular machine. We also consider initial setup times, that the initial setup times are before the first task of the machine can be scheduled. So this would be the solution graph for the flexible job shop with sequence-dependent setup times. Okay, these are the constraints of the problem in a more formal way. For example, we have the no preemption constraint, and that's when you are processing a task, that task cannot be interrupted until the task is finished. The objective is to find the starting time for each one of the tasks of the program, so that the schedule is feasible, and we want to minimize the make span. The make span is the ending time of the last task to end. Okay, let's talk a bit more about the solution graph model. To build the solution graph model, we have to first solve the assignation subproblem, which is for each task of the instance, select the machine which is going to process it. Afterwards, for each machine, we have to select the order in which the tasks are going to be processed in that machine. The sequencing decisions, we have to make the sequencing decisions carefully to avoid cycles in the final graph. If there is a cycle in the graph, then the schedule is not feasible. In the classical job shop, there is only the sequencing subproblem. In the flexible, there is the assignation and sequencing, and that's why the flexible job shop is much more difficult than the standard, the classical job shop. This is the Gantt chart, which is the visual representation of the schedule. We can see the starting and ending times of each task of the instance. And now, some very important concepts about the solution graph. First of all, the critical path is defined as the path with the longest cost from the start node to the end node. In this example, we have this longest path in pink, and the length of the longest path corresponds to the main span. Then a critical block is a subsequence of the critical path such that all the tasks require the same machine. In this example, we have these two critical blocks of length 2. And finally, a critical arc is an arc inside a critical block. Okay, these concepts of critical paths and critical blocks are very important because most neighborhood structures in the literature and a lot of properties rely on the critical path and critical block. Now, based on this rough model, I am going to describe the neighborhoods used to solve this problem. We propose a neighborhood which is the union of two smaller neighborhoods. One of them is defined to tackle with the assignation subproblem, and the other is defined to solve the sequencing subproblem. I'm going to describe each one of them separately, starting from with M1S, which is the one designed to solve the sequencing subproblem. This structure is based on reversing critical arcs. So here we have a small example with 3 jobs and 2 machines, and the critical path marked in bold, with a main span of 4. So we have to consider the reversal of the critical arcs in that path. We can create one neighbor reversing this arc to create this schedule, and we also can create another neighbor reversing the other critical arc to lead with this other schedule. We can see that the neighbors can have lower or higher main span than the initial schedule. Okay, to do a more efficient structure, we also consider some non-improvement conditions. The first proposition simply shows that reversing a non-critical arc cannot lead to an immediate improvement in the main span. That's why we only reverse critical arcs. Proposition 2 gives another fast non-improving condition, so we can quickly discard some of the non-improving neighbors. This is to make the structure a little more efficient. There is another concern, and that is reversing an arc can lead to an unfeasible schedule. Let us suppose that these tasks B and W are consecutive tasks in a machine, and we want to reverse this arc, the arc from B to W. And let us suppose that there is an alternative path from the job successor of B to the job's predecessor of W. If that path exists, then the neighbor will have a cycle, so it's going to be non-feasible. This proposition gives a sufficient condition for these alternative paths not existing. So we can ensure then that the neighbor is feasible. This condition is very fast to evaluate and it's very accurate. Okay, as for the other structure that tackles with the assignation subproblem, the structure is based on changing the machine assignation of one of the tasks in the critical path. Then, in this example, again we have the critical path in bold, and one of the possible neighbors is to take this task, which is actually in machine 1, and change it to machine 3. And that would produce this neighbor schedule with a main span lower than the original schedule. This is because machine 3 was underused in the initial schedule, only processed one task, and now processes 2 tasks, is more balanced, so the main span is lower. Okay, when we change the machine assignation of one task, there is one decision to make. In which position of the new machine we have to insert the task. In this work, we choose to insert the new task in such a position such that the topological order of the graph is the same before and after the move. In this way, we can prove that the resulting schedule is always feasible and can produce improvement. The number of networks created with this structure depends on the length of the critical path and on the number of machines which can process each of the tasks. Well, finally, when we have all the neighborhood generated, we have to choose one of the neighbors. Computing the exact makespan for all the neighbors is computationally costly, so we propose to use estimation procedures. In particular, we extend some procedures used in a previous paper. They are lower bounds, they are fast to evaluate, and they are very accurate. In fact, it's like in 90% of the cases, the estimation, it was exactly like the real makespan of the neighbor. And I'm going to describe the meta-heuristics used to solve the problem. It's a genetic algorithm combined with tabu search. A genetic algorithm is based on maintaining a set of solutions to the problem and evolving through a number of generations. Hopefully, along the generations, the solutions are going to be better and better over time. For chromosome representation, we use the two-vector representation, which is typical in the flexible job shop. One vector for the sequencing subproblem to indicate the ordering of the tasks, and one vector for the assignation subproblem to indicate which machine for each task. In the next slide, I'm going to show you an example of the algorithm. First of all, an initial population is generated at random. In this case, the initial population of 6 chromosomes. Then the initial population is improved with the tabu search. Now we have some improved chromosomes. And then steps 3 to 6, we repeat the steps 3 to 6 until a stop condition is met. Okay. Step 3 is group randomly the chromosomes of the population in pairs. Then, for each one of the pairs, we apply the crossover operator. For crossover, we use an extension of the classical JOX operator. It takes 2 parents and creates 2 offspring with characteristics from both the parents. Then, for each pair of solutions, we apply the crossover and generate 2 offspring. Then, we improve each of the offspring with tabu search again. And finally, for selecting the chromosomes for the next generation of the genetic algorithm, from each group of 2 parents and 2 offspring, we select the 2 best solutions to advance to the next generation. Now we have the new population of the algorithm, and we should repeat this process for the number of generations we want. Now for the tabu search algorithm. Briefly, high climbing local search methods, you know, that have the problem of local optimums. The tabu search is an advanced local search technique that can choose neighbors worse than the actual solution, and so we can escape from local optimums. The main structure that the tabu search uses for doing that is the tabu list, which stores the last arcs that have been reversed, and to avoid that these arcs are reversed again soon. We use a dynamic length for the tabu list so that we reach a balance between intensification and diversification. When we have all the neighborhood generated, we have to choose then the neighbor with the best estimated makespan, but discarding tabu neighbors. Finally, for the experimental study, first of all we did a small parameter tuning and we set the population in 100 chromosomes, stopping criterion of the genetic algorithm 20 generations without improving the best solution, and double search stop criterion in 400 iterations without improving. As this is an stochastic algorithm, we run it 10 times and record the best and average make span. In this graph we show the convergence pattern in one of the runs. We show the make span with respect to the generation number. We can see that the convergence pattern is good. First, about the flexible job shop with stubs, we compared against a method created by Angelo Odi et al. In a set of 20 instances. For performance measure, we use the mean relative error, which is the percentual error with respect to a lower bound, and the number of instances for which a method reaches the best known solution. Okay, here are the results. The column IFS shows the mean relative error from Angelo Odi, then the results from the genetic algorithm alone, the results from the tabu search alone, and the results from the hybrid algorithm. We show the mean relative error and in parentheses the mean relative error of the average solution. So the best and the average. And in the final column, the time in seconds of a single run. First of all, we can see that the hybrid algorithm is much better than both the genetic algorithm and the tabu search alone. So we can see that the synergy between the meta heuristics is good. The mean relative error is the lowest, and the number of best solutions found is the highest one. It's 18 instances of the 20 total instances. Also, compared to the method of Angelo Odi, it's also better with a lower mean relative error and higher number of best solutions. But the flexible job shop without setup times is a problem much more widely studied, so we can compare it more benchmarks and with more methods. In this case, we have compared against the state-of-the-art, 3 methods from the state-of-the-art, which are the tabu search from Mastroianni and Gambardella, a hybrid genetic algorithm from Gao et al., and a discrepancy search method from Miguel, in 3 different benchmarks. Well, rightly we can see that the mean relative error, if we consider the average of the 3 make spans, is a little lower, a little better than the other methods. It's the column in red. And we are able to obtain the most number of best known solutions with 34 of the total of 49 instances. In particular, we were able to improve the best known upper bound in 9 of the 49 instances. Finally, for some conclusions, first of all, I have built the graph model, then I define a neighborhood based on that graph model, which is the union of 2 neighborhoods, one for the sequencing subproblem, one for the assignation. That these neighborhoods are embedded in a memetic algorithm, which is genetic algorithm plus tabu search, and the experiments show that the results are very good, improving over the state of the art and obtaining new upper bounds for a number of instances. For future work, well, first of all, experimenting across more benchmarks and even defining one new benchmark with set of times, because there are not many benchmarks. We would like to use bigger instances and more complicated instances. Also try different crossover operators and implement a scatter search method with path linking. And finally, to extend this approach to other problems, like considering fuzzy durations for the tasks. Well, right now my work is on solving the job shop with time windows. And that's all. Thank you very much.